Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. We've been talking a lot about angle relationships in circles up to this point. This lesson is going to focus on segment relationships and us coming up with different formulas and finding the measures of different segments, whether they be tangent, secants, chords. Won't do too much with radii or diameters today, but just different types of segments in circles. Let's jump right in. We're going to skip the do now today. I think we have enough to do other than that. We're going to look at our first theorem. This is called the chord-chord product theorem. What I'd like you to do is pause the video, read the theorem, look at the diagram, and then see if you could come up with a conclusion. Notice the conclusion box is blank. That's because we are going to fill it in ourselves. So pause the video, see if you could fill that in based on what the theorem says. Okay, so it says if two chords intersect in the interior of a circle, then the products of the lengths of the segments of the chords are equal. The products of the lengths of the segments of the chords are equal. So we have chords A, B, and C, D. They intersect at E. I think you actually may need to see this one. You may not have been able to come up with a conclusion just by reading it, because I don't think it's that clear from the way the theorem stated. But essentially, we're looking at the pieces of AB. So AE times EB, those two lengths, that's going to be equal to CE times ED. So if you multiply each piece of the chord together, that's going to be equal to the product of the other pieces of the other chord. Let's apply this to one practice problem down below, pretty straightforward one. See if you can find the length of x. Pause the video, see if you can find the length x or SQ. Okay, so I have the chord PR. So I have 6 times 4, and then my other chord is ST. Those two pieces are 8 times x. That gives me 24 is equal to 8x, which gives me x has to be equal to 3. So SQ is equal to 3. And of course, you can have a much more challenging diagram where this is just one of the theorems that you would need to use to find a missing segment, right? And we'll look at more of those in class, but we're just focusing on the basics right now. What I do want to do is actually go through a proof for why this works. So we're going to skip these two tougher practice problems, and we're going to go to this proof. Okay, pause the video. See if you can fill in the reasons for this. You may have to add some segments to your diagram to be able to see what they're talking about. Okay, first one is given. AD and CB intersect at point E. Then it says draw segment AC and segment BD. So there's no justification for that. We just say, 2 points determine a second segment. You could also say by construction, because all we've done is connect those 2 points. That's why I gave you that reason, because it's not really one I want you to have to think too hard about. Our next statement says angle AEC, we do those in blue, AEC is congruent to angle BED. Well, those two angles are vertical angles, so vertical angle theorem would be accurate here. Our next statement says measurement of angle ACB is equal to 1/2 the measurement of arc AB. So ACB is this angle right here. That's going to be equal to half of this arc. We know that by the inscribed angle theorem, right? ACB is an inscribed angle, so it's 1/2 the measurement of the intercepted arc. And it's actually the same reason for the next statement. This one we have BDA. Let's do that one in orange. This angle Same arc. All right, it's going to be half the measurement of arc AB because the intercepted arc is the same as it was for angle ACB. Well, if both of those are equal to half the measurement of arc AB, well, they've got to be equal to each other by the transitive property of equality. Transitive POE. If I know two angles are equal in measurement, I know that they are congruent by the definition. My spelling is still not great. Definition of congruent angles. Not angels, angles. Now I can put in some congruency symbols here. Let's do those in blue as well. Oh, that's orange. Well, now I notice that those two triangles share two sets of congruent angles. So by the AA property of similarity, they are similar. And if two triangles are similar, well, I can say that their sides, their corresponding sides, will have the same ratio. So ED to AC, ED to EC, and BE to AE, that ratio should be, those ratios should be equal by the definition of similar triangles. Right, if two triangles are similar, they'll have the same scale factor, which means corresponding sides will have the same ratio. Well, to finish it off, we're just going to cross multiply, or multiplication property of equality. And then we get what we want. Right, if I erase this, what I have in my diagram to kind of clean it up a little bit, right, I've proven that AE times ED, which are the two segments that make up that chord, those are going to be equal to the product of CE or EC times BE, which are the segments that make up the red chord. So there's a proof of the chord-chord product theorem. All right, two more theorems today. One is called the secant-secant product theorem. One is called the secant-tangent product theorem. Same thing as before. Go ahead and read the theorem and see if you're able to come up with a conclusion. Your conclusion is going to be an equation for both of them. So reread the theorem maybe once or twice, look at the diagram, and write your conclusion in the form of an equation. So the secant-secant product theorem says if two secants intersect in the exterior of a circle, so here they intersect at point E, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. And I think this kind of says it right here. Whole times the outside is going to be equal to whole times the outside. So we have two secants, AE and CE. So AE, that's the whole, times the outside part, which is BE. That's got to be equal to, and we're talking about this secant here, that is going to be equal to the whole of the red secant, so CE, times the outside portion of the red secant, which is DE or ED. So that will always hold true as long as two secants intersect outside the circle. The secant-tangent product theorem is similar, except they're using one tangent instead of two secants, so one tangent, one secant. This says if a secant and a tangent intersect in the exterior of a circle, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. And again, I think it's nice to look at what they have in parentheses here. Whole times the outside of the secant is just equal to the tangent squared. So if I have this secant AC, just like it was for the top, I've got AC times the outside, which is BC. for my tangent, I don't have two parts, right? I just have the outside part. So that becomes CD squared. So very similar. The tangent one just has one segment though, so there's no outside times the whole. The outside and the whole are the same, which means we're going to be squaring. Okay, let's apply this again to, we'll do number 1. Pause the video, see if you can find the measurement of x. Okay, so my first secant, we'll do that in red, RT. I guess maybe you're thinking, well, Mr. Fussett, don't secants have to be lines? By definition, yes. So this red is just a piece of a secant, right? Technically, we would say if it's a secant, it would extend. So we're just looking at a piece of a secant, but for these problems, it means the same thing essentially, right? We're looking at a length, which means we can only look at a piece of a secant, right? If this was a line, we would not be able to figure out the length of a line. So we're just looking at a piece of a secant because we're just looking at a segment. Enough of that little tangent, I guess pun intended there. Does that work though? Because I was talking about a secant. I don't know. Anyway, back to the actual math. The entire length of that red secant is 10. The outside part is 4, so I get 10 times 4. The other secant, the entire length is 5 plus x, and the outside piece is just 5. Now we just need to simplify. I get 40 on my left-hand side. Distribute this 5 to both. That gives me 25 plus 5x. Subtract 25 from both sides. I get 15 is equal to 5x. And I get x is equal to 3, which coincidentally was our answer to the other one we did on video. Okay, let's move on to the proof, and that's what we'll finish with. This video is going to be a little shorter than normal, which I'm sure you're okay with. We're going to prove the secant-secant product theorem. See if I can squeeze the whole thing in. There we go. Okay. So like always, pause the video, read through the statements, take a look at the diagram while you're reading through to try to make those connections, and then fill in as many reasons as you can. Okay, so it says segment MP and MK are secant segments of circle Q and intersect circle Q at points N and J respectively. That's given. Just like our last proof, we're going to draw in some extra segments here, some auxiliary segments. PJ and KN. PJ, KN. Oops. And we're just going to say 2 points determine a segment. You could also say by construction. Our next one is angle M is congruent to itself. Put a little congruency arc up here, but we should know that that is the reflexive POC, reflexive property of congruence. I'm then told that the measurement of angle MPJ, that is this angle right here, just a little sliver there, MPJ is equal to 1/2 the measurement of arc NJ. Go do that arc in orange. Well, that's the inscribed angle theorem, right? MPJ is an inscribed angle, which means it's half the length of the intercepted arc. I then have another inscribed angle, MKN. Another sliver here. And that has the same arc, right? I'm just going to leave it up here in orange, but it has the same arc NJ. So again, this is just another inscribed angle theorem. If those two angles are equal to the same measurement, or half the measurement of the same arc, well, then they're going to be equal to each other by the transitive, transitive POE. You'll notice this proof is very similar to our last one, right? If those angles are equal in measurement, they are congruent by the definition of congruent angles. Let me put those little congruency arcs in there now. And you'll notice we have two triangles that are similar. Let me outline them for you. We have MPJ, so this one in lime green, and we have this one in brown, MKN. So they do overlap a little bit here. And we need to put two little arcs right here. So by AA, those triangles are similar, AA similarity. If I have two similar triangles, I can say that the corresponding sides of those triangles must have the same ratios, right? Because the triangles are going to have a scale factor that's constant between all three of the sides. And this is just the definition of similar triangles. So MP over MK has got to be equal to MJ over MN. I just need to cross multiply to get what I want. MP times MN is equal to MK times MJ. And let's take a look at this right here, right? For the secant-secant product theorem, let me erase what we have up here. I need the whole secant, so MP, which is the whole secant, times the piece that's outside, MN. Well, that works. That's what I want. For the other one, I need the whole secant, MK, which is what I have, times MJ, which is the outside, which is also what I have. So secant-secant product theorem, here's your proof. All right, that is going to do it for this video. As always, enjoy the rest of your day, and we will look forward to seeing you next time, which will probably be for the last lesson in our circles unit.